All right, so we are going to move on with the graphs of sine and cosine. We'll go ahead and do that in about a minute. So if you've not taken out your notes, go ahead and do so. And while you're doing that, just a couple of housekeeping items that we need to take care of. The big one, of course, is next Thursday on the 15th. That's when your first exam is going to be. So it'll have the law of cosines, it'll have the law of sines, it'll have area of oblique triangles using Heron's formula, and also the side angle side scenario. And it's also going to have information from graphing sine and cosine. Now, we are going to be able to start the next lesson, which is graphing the other four trig functions, but I did not put that on the test. Okay, so that's coming up next Thursday on the 15th. We definitely want to be looking ahead to that. This Thursday, I'm going to go ahead and pass out the homework for this current section. It's going to be due on Monday. We'll kind of see how things play out. Bless you. Hopefully we'll have a little bit of time in class to go ahead and work on it. I don't want to go ahead and say definitely that'll happen now because I don't know how far we're going to be able to get. But hopefully that'll happen. Now, something else is happening on Thursday. Okay, you're going to have first quiz of the 6 weeks, but it's not going to be over graphing sine and cosine. It's over the two laws, law of cosine, law of sines. Okay, so make sure you're familiar with those. It's going to be a couple of word problems, so I'm not anticipating too many problems, I'm hoping. Let's see, what else? Tomorrow I'm not going to be here. I will be on campus, but I have some IB interviews to take care of. So I'm leaving a worksheet with the substitute over evaluating trig functions on the unit circle using the special right triangles that we've been working at. Okay, so if you're still having trouble with that particular concept, this is a perfect opportunity to go ahead and practice it. I'm going to encourage you to work together, help each other out. I will be posting the answers to the worksheet you're going to get tomorrow to the website so you can also check your progress. Okay, because what's going to happen, the end of this week, Thursday, Friday, those happy minutes are going to be recorded as homework grades. Then next week, we're back to recording them as quiz grades. So because it's really early in the 6 weeks this time, that can either really help you out or it can kind of drag you down. So we want to make sure that everybody feels really good about those. I believe that's all I got, unless anybody has any questions. Hey, Zach. It's still going to be the exact same idea. I'm just going to give you a radian measure. You'll find me the reference angle, create the triangle, evaluate the trig functions. Okay, so at the end of this week, all next week, it's going to be the same. Okay. All right, anything else? Now, if anybody knows for sure they are not going to be here on Thursday and or Friday, just come talk to me. I've already got the copies. Or if you do happen to miss those days, please, visit the website. Okay, go ahead and get all the materials you need. All right, well, let's go ahead and talk about sine and cosine. So we kind of went through sine yesterday. We talked about all his characteristics. Let's see, we had 5 critical points that we really wanted to look at. Sine starts with a 0, then a maximum, 0, minimum, and then we go back to a 0 because this right here, this curve represents one cycle for sine. Now, both sine and cosine, what's their period? Yeah, it's 2 pi, right? That's the number of radians necessary to complete one cycle. Oh, is that enough? Does anybody else need the key? Okay, so there we go. Now, one of the things we mentioned was the domain of this graph. We haven't gotten to cosine yet, but sine's domain is all reals. So why is it all reals? How am I able to just continually go forever? How is this connected to the unit circle? What's that? The coterminal angles. Like, what do you mean? That's exactly right. Every revolution is one cycle, one period for your graph. So, for example, sine, if I go ahead and start here in standard position, one rotation, well, that's one cycle. Okay, that's 2 pi because I rotated 2 pi radians. Well, if I rotate again, well, then that's just another cycle. And I can continue to do this, as many times as I want. I can rotate an infinite number of times. Now, I can also rotate clockwise. So if I were to rotate clockwise, okay, go back in the other direction, well, I'm still going to get that just going in the other direction, okay? The one thing, though, that I did bring up, and we're actually going to go ahead and start to talk about it today, that probably didn't mean a whole lot to you yesterday, but is going to be super important to you today. What about these horizontal distances between the critical values? They need to be what? They need to be the same. Okay, these distances, we're going to go ahead and divide them up. In fact, I'm just going to go ahead and tell you now, we're going to be dividing these periods by 4. Now, you'll see why in just a little bit. Okay. Then we talked about some characteristics. We had to come up with some expressions for the x-intercepts, maximums, and minimums, because with the domain being all reals, we have an infinite number of those. Okay. And then we had those key points right down here that we listed. So sine starts with a 0. Then we have our maximum, 0, minimum, and then a 0 again. You know, notice we're referring to the y values of each of these. Okay. All right. And then we started in with cosine, and you guys, whoa, had a seizure. Okay. Cosine, you guys helped me by rotating around the unit circle, find the points. But cosine, his cycle starts with a maximum. Then we go to a 0, minimum, 0, maximum. In fact, he looks like the curvy V. The one thing we haven't gotten to about cosine just yet is going to be his characteristics. So what do you think his domain is? Yeah, it's all reals. For the same reason sine is all reals, we can rotate both clockwise and counterclockwise an infinite number of times. So negative to positive infinity. What about the range? How tall is he? Bless you. Yeah, he's bounded above and below. The maximum is 1, the minimum is -1. So I'm going to go ahead and include these. So -1 to 1. All right. Now, just as with sine, cosine is going to have an infinite number of x-intercepts, maximums, and minimums. Okay, let's go ahead and start with the x-intercepts. If I'm looking at the graph of cosine, okay, the first x-intercept, the first 0 I have is at pi over 2, right? Well, how many radians will it take before I get to the next 0? Okay, what's that? Not 2 pi. It's just going to be pi radians, right? Okay. So if I take pi over 2 and add pi, I'm at the next 0, the next x-intercept. Well, how would I get to the next x-intercept? What would I do? Okay, Christian? So I started at pi over 2. In order to get to the next intercept, I added pi. So how do I get to the next intercept from 3 pi over 2? Wouldn't I just add another pi? So plus pi, there's an x-intercept. Plus pi, there's another x-intercept. And I can continue to do that forever and ever. So how does that help me come up with an expression? Wasn't this the class that was using n? Okay. So it looks like we're just looking at multiples of what? Or I should say adding multiples of pi. So the x-intercept, we started at pi over 2, and we're going to add pi n. We just want to go ahead and make sure that we're writing down n is an integer. So we would say plus pi times 1, plus pi times 2, plus pi times 3. We can even go the negatives. And also we want to make sure that it works for pi over 2. So plus pi times 0 would be at pi over 2. Okay. What's the y-intercept? Yeah, that's just 0, 1. Okay, that's easy. There's only one y-intercept for the parent. Now, we know the maximum is 1. We know the minimum is -1. But we want to come up with an expression for where those occur. So we're going to do just like we did yesterday. We're going to write them as ordered pairs. Okay. So think about it. We just said that the period was what? What's the period for cosine? 2 pi. So it repeats the same pattern, this curvy V, every 2 pi radians, right? So if I start here with a maximum, it's going to be 2 pi radians before I get to the next maximum. Then 2 pi radians before I get to the next. And then the next. Okay? So write out what you think a general expression would be to find any of those maximums. And then if you're feeling ambitious, go ahead and do the same thing for the minimums. Give you a few seconds to go ahead and look that over. Okay, for the maximums, does anybody want to share what they got? Okay, so enhance, Satish.
0 plus 2 pi n.
There you go. 0 plus 2 pi n, and then we have 1. Now, did anybody just go ahead and put 2 pi in? Okay, because what is 0 plus 2 pi n? Still just 2 pi n. But if you want to go ahead and start with that first maximum, you are free to do that. That's absolutely fine. Okay, good, good, good. We just, again, want to make sure we list that n is an integer. Okay. What about the minimums? I'm sorry, Aiden? That's exactly right. Pi plus 2 pi n, comma negative 1. Because, see, you always have to start with our first x-intercept, our first maximum, our first minimum on the cycle we're looking at. So if I come over here, the first minimum we've got listed does occur at pi. And just like the maximum, we're not going to get to another minimum until we go 2 pi radians. There we go. So I'm just going to say n is an integer again. Okay, how many people got both the maximum and the minimum expressions correct? Okay, that's good. That's good. All right. Is it continuous? Yes, absolutely, just like we talked about yesterday. Is it bounded above? Yes, maximum of 1. Is it bounded below? Yes, minimum of negative 1. What did it mean even in odd symmetry? What was even? Okay, say again what? Over what? What axis? The y-axis, yes. If I can fold the graph along the y-axis, if two parts come together perfectly, that's even symmetry. What does odd mean? That means rotational symmetry. How far would I rotate it? 180 degrees. So if I'm looking at the graph of cosine, can I fold it along the y-axis, or would I rotate it to be symmetrical? Fold it. If I fold it along the y-axis, these two parts are going to come together perfectly. If I rotated him, I would not end up with the same graph. In fact, this maximum would be this minimum. All the maxes and mins would essentially flip. Okay. So this one is even. So we have symmetry with the y-axis. Okay, and then we have our key points. Now remember, these key points are coming from the graph where we listed the max, the 0, all the way back to the max again. So cosine starts with a maximum, which is 0, 1. Okay. And then we reach our first 0, which is located where? Pi over 2, 0. Then we have our first minimum, which is going to be at pi negative 1. Then we're back up to the x-axis, but where? Now, it definitely will be 0, but what x does that occur at? 3 pi over 2. And then we finish up with the maximum, 2 pi. There we go. Now, remember, one other thing I'm going to go ahead and bring up. The horizontal distance between these 5 critical points have to be the same. They've all got to be the same distance. That's why we're always going to divide our periods by 4. Okay, now you'll see what I mean in just a second. All right, well, let's start some transformations, starting with amplitude. And you probably heard about this in your other classes. We can change the height or the amplitude of the graphs of sine and cosine functions by transforming the equation of the function. This is going to change the range of the parent. Okay, now when we're talking about transformations, we're referring to those transformations that you were originally shown in Algebra 2. So we're talking about shifts, both horizontally and vertically. We're talking about horizontal and vertical dilations, stretches and shrinks, and reflections. Okay, so we're going to be applying all of those to these trig functions. Now, anything affecting x directly, anything inside the trig function is going to be horizontal. Anything outside, not affecting x directly, that's going to be vertical. So what do you think about 2 sine of x? Vertical or horizontal transformation? Definitely vertical. It is not affecting the x. Nothing is happening horizontally. What kind of transformation is that? Is it a reflection, a dilation, or a shift? It's not a shift. It's dilation. Now, look at the operation. If it's a shift, then you have to be adding or subtracting. If it's a dilation, what do you have? You're multiplying. See, we have 2 times the sine function. All right, so is this going to be a vertical stretch or a vertical shrink? Okay, it's going to be a stretch. That scale factor is bigger than 2, so we're going to stretch this guy. Now, I always go ahead and start with the original graph. So let's start with sine. So sine has a minimum, maximum, excuse me, 0, maximum, 0, then a minimum, and then back to 0 again. Now, you don't have to do this. Every time I transform a function, I got in the habit of drawing the parent first. Okay, if that's something that helps you, great. If not, you don't have to worry about that. Well, the parent here has those 5 critical points that we were looking at yesterday, right? Well, the 2, we're only affecting the y values. Okay, like for example, this point right here is 0, 0. That y value of 0, what's 0 times 2? 0. So he's going to stay right where he is. The dilation is not going to be able to affect him. In fact, any point that's already on the x-axis is going to remain anchored there. Okay. But now look at this one right here. This point is pi over 2, 1. Okay. The 2 is only affecting this graph vertically, so I'm only going to be paying attention to the y value. So what's 1 times 2? 2. So this guy is going to be pulled up to 2. Just the same way this minimum over here, the negative 1 times 2 gives me negative 2. Okay. There we go. So see, I affected him vertically. I multiplied the original graph sine by 2, so I stretched him vertically by 2. Is this starting to come back to you guys, the transformations? Okay. All right, let's go ahead and try the next one. Now, I'll start by graphing cosine, just the parent graph. Now, remember, cosine always starts with a maximum. Then we have a 0, a minimum, a 0, and a maximum. Remember, one cycle of cosine looks like that curvy V, right? So there are actually 2 transformations happening here. Okay, can anybody tell me what one of them is? Okay, Satish. Okay, just like before, it's being vertically stretched by 2. We are not affecting the inside, the x. We are outside the function. Okay, now, the thing about transformations, you really don't want to look at that as a negative 2. Think of it as a negative and a 2. The 2 is still going to stretch it, just like the previous graph, but what's the negative going to do? It's going to reflect it. The negative's one job is to reflect it. If it's outside, as this one is, it's going to reflect it with respect to the x-axis. Okay. So let me give you a few seconds to go ahead and take a look at that one right there. Okay. And then we'll go ahead and come back together and try it. Okay, are there any points, just like the previous graph, that are going to remain where they are? The transformations won't seem to affect them? Yeah, because these y values of these x-intercepts are 0. 0 times negative 2 is still 0. Okay. So this point right here at 1, it'd be stretched to 2, but then the negative would reflect it. This minimum here, negative 1, would be stretched to negative 2, but then the negative would reflect it. Basically, all you're doing is multiplying the y value by negative 2 here. And then the same thing, 2 pi 1 happened at 0, 1. So this guy would be down here. So you should end up with a graph that looks like this. So it's a taller V, but it's just been flipped. Okay. How many people got that right? Okay, that's not bad. That's good, good, good. Now, somebody help me out. The amplitude of both of these graphs is what? Okay, Aiden is telling me 2, and she is absolutely correct. The amplitude is half your height. So for the original graphs, the amplitude is always 1 because they're always 2 units high. These guys are 4 units high, so the amplitude is going to be 2. So how do we go ahead and find that easily? Well, we simply take the absolute value of that leading coefficient. Whatever we're multiplying the trig function by, we take its absolute value. Okay. Now, there's one exception, of course. When the value of a is less than 0, that means when it's negative, that's just going to result in a reflection. Remember, the negative's one job when you transform is to reflect. Does anybody know here the negative was outside, so it reflected it with respect to the x-axis? How could I reflect a graph with the y? Okay, Aiden, what do you think? Where would the negative have to be? It would have to be negative x. That's absolutely right. Okay. All right. Well, let's try something else. That was the amplitude. Let's try the period. Okay, we've already established that the period of a parent sine or cosine graph is 2 pi. Let's explore how the general form of the equations can change the period of the graph. Okay, so take a look at these. I've got sine of 2x and I've got cosine of 1/2 x. Okay. Am I affecting these vertically as the previous examples, or are they horizontal? Why are these horizontal now? See, it's inside the function. I'm affecting x directly. We have something actually connected to x. But this is where it gets a little strange. When you transform horizontally, you have to think of certain rules. Okay, I'm still dilating, right? Because it's still 2 times x, it's still 1/2 times x, but what am I thinking of? When you multiply inside, you have to do something. Does anybody know what I'm talking about? Okay. When you multiply by x, you have to take the reciprocal. The reciprocal is the true scale factor. Write it out. Yeah, that's supposed to be a C. Right. There we go. You have to take the reciprocal. Okay. And we'll kind of talk about that as we go along. But let me go ahead and start with sine. I'll just graph sine's parent. Remember, sine always starts with a 0. Then we have a maximum, 0, minimum, 0. Okay, so there's sine, using those 5 critical points that we keep talking about. Okay. Now, here's the thing. I'm going to go ahead and show you to transform these in a particular way. There are other ways, but I think this is probably the best and most efficient. What's the period for sine? It's always 2 pi, right? So what you're going to do, whatever is inside your trig function, you're always going to put that in a compound inequality between 0 and 2 pi. So I'm going to say 0 less than or equal to, less than or equal to 2 pi. So whatever you're given, that's what you're going to go ahead and put between 0 and 2 pi. Now, solving this compound inequality is going to help you figure out what the period is. Okay, how wide this guy has to be. So how would I solve this for x? How would I get x alone in the middle? Yeah, go ahead and divide by 2. Now, it's got 3 parts, so whatever I do to the middle, I got to do to the outside parts. So 0 divided by 2 is 0. Less than or equal to x, less than or equal to pi. Okay. So now remember, the period tells me how long it's going to take to complete one cycle, okay, for sine. So how long should it take to complete that cycle? It's just going to be pi units. Okay, now we'll do a little something else in just a second here. But here's what we're going to go ahead and do. I'm going to go ahead and list the 5 critical values for sine. Now this is on the back, or excuse me, the front of your paper. right at the very bottom. You remember those 5 critical points for sine? I'm only interested in those y values. So I want 0, 1, 0, negative 1, 0. I'm going to come back over here to my paper. And I'm just going to write this over to the side over here because I don't have much room. So sine always starts with a 0. Then we have our maximum, 0, minimum, and we go back to another 0, right? Well, the lower boundary of your compound inequality, the 0, you're going to match it up to the very first one here. The upper boundary, you're going to go ahead and match it up to the last critical value right there. What you're doing is creating points on the transformed function. So see, I already know for sure that the coordinate 0, 0 should be on my graph. I also know that pi 0 should be on my graph as well. Now, you remember there's something I brought up today and I brought up yesterday. What should we do for the horizontal distances between these critical points? Should they always be the same or different? They should always be the same. What we want to do is always divide this distance by 4. Because between the 5 critical points, you're always going to have 4 distances. Well, help me out here. How far is it from 0 to pi? It's just pi, right? So whatever that distance is, I'm always going to divide it by 4. This is what I need to add over and over again to fill in the rest of the points. So what's 0 plus pi over 4? Pi over 4. Again, what's pi over 4 plus pi over 4? Pi over 2, right? Because that would be 2 pi over 4. Now what's pi over 2 plus pi over 4? 3 pi over 4. And now let's go ahead and check. This should always happen. What's 3 pi over 4 plus pi over 4? Does that give me pi? Yes. So you see, you've got ordered pairs for one full cycle of this graph, this function. So I know that the next ordered pair should be pi over 4, 1. Now pi over 4 is going to be halfway between 0 and pi over 2. So we have this point here. Then we have pi over 2, 0. Then we have 3 pi over 4, negative 1. And we already took care of the pi 0. Well, look. What happened? What graph did we end up with compared to the original? Was it bigger or smaller? It's a shrink, right? Remember, what was the key word I said? When you multiply by x, you have to take the reciprocal. We'll take a look. We're multiplying x by a 2. What's the reciprocal of 2? Half. This graph is half as wide as the original was. And here's what's really nice about this. Once you know what the pattern is, I know exactly what the points are going to be for a cycle. You can now create as many cycles as you want. I know that the next one would have to be a max, then a 0, then a min, and then a 0. Once you get one period of the function graphed, you could then just basically copy that over and over again as many times as you want. Okay, how we doing? Okay. Now, the first time is always a little strange, okay, because it's something new. Let's try it again, okay? But now we kind of know what to expect. This time I want a cosine of 1/2 x, okay? Let me go ahead and take this off. All right. So just like sine, cosine has a period of 2 pi, right? So I'm going to start with 0 is less than or equal to 2 pi. What do you think I'm going to put between 0 and 2 pi? X over 2. Whatever I'm given inside the function is what's going to go between 0 and 2 pi. Every single time for sine and cosine. Okay. Now what? Yeah, we want to multiply through by 2 because we want just x in the middle, right? So 2 times 0 is still 0. Less than or equal to, there's the 1x that I'm looking for. Less than or equal to 4 pi. So what's my period now? Shouldn't be double, should be 4 pi. Okay. Now, you remember the values over here, the critical values that we used for sine? Remember, he starts with a 0 maximum, 0 minimum, and then goes back to a 0. Why do I not want to use those here? What's different? See, those are the values for sine. We're now graphing what? Cosine. So that's the one thing you got to be careful about. We want the y values from cosine's critical points. So we want his maximum, 0, minimum, 0, maximum. Okay, so I'm going to use these guys here. I'm going to go ahead and say maximum, 0, minimum, 0, maximum. So you need to be careful and use the correct values for the correct function. Okay. Well, the lower boundary was 0, so I'm going to pair that with the very first one here. The upper boundary, I'm going to go ahead and pair that with the last one here. So see, right away, I already know that 2 points on my graph are going to be 0, 1, and what? 4 pi, 1. Okay. Now, try this one on your own for just a second. The distances between these critical points have to be the same. So we're always, always, always going to divide by what? 4, because we have 4 distances. So write out what you think these other values should be. And while you're doing that, I'm going to go ahead and fill in just the cosine parent, just the parent. So he starts at, he has a max, 0, min, 0, max, 0, min, 0, max. So this right here is just the cosine parent. Okay. Now, for the people who are still having a little bit of trouble, how far is it from 0 to 4 pi? Well, the distance is 4 pi, right? And we always want to break it up into how many distances? We always want 4. So what should I be adding over and over again this time? Just pi. So 0 plus pi. Plus pi. Plus pi. And again, just like before, will 3 pi plus pi give me 4 pi? Okay. But now you've got 5 ordered pairs on your transform function. I know I should have a point at 0, 1, pi 0, then 2 pi negative 1, then 3 pi 0, and then 4 pi 1. I'm just going right through these right here. What happened? This was horizontally stretched. Why did this result in a stretch? You have to take the reciprocal. When you're multiplying by x, you multiply by the reciprocal. See, in the first one, we had 2x, but the reciprocal was 1/2. So the graph is half of what he originally was. Here we have 1/2 x, but the reciprocal of 1/2 is 2. So the graph should be twice what he originally was. Now, one other thing I want to go ahead and mention, have I done anything to the critical values for the y's? Why did I not change them at all? Well, let me ask you, what transformations were occurring vertically for these two graphs? There's nothing happening outside. There's no vertical, so there's no reason to change them. But if something was happening vertically, would those change? Yes. Okay. So how do we go ahead and figure out by looking without graphing what the period's going to be? Here's the formula. It's 2 pi divided by b. B is the coefficient of x in your function. Okay. That's how you're going to find the period. So for example, what's the value of b from sine of 2x? B equals 2, right? So plug 2 into this formula. What's 2 pi divided by 2? Pi. Isn't that what the period turned out to be? Same thing over here. What's the value of b for cosine 1/2 x? 0.5. So 1/2, right? Plug that into my formula. 2 pi divided by 1/2, what happens when you divide by a fraction? You multiply by the reciprocal. Did the period turn out to be 4 pi? Yeah. Is this starting to make sense? Anybody have any questions? Okay. Now, before you start to put up, okay, hang on. Okay. Let me show you this very quickly. I'm just going to go ahead and mention this. Now, phase shift. That's just a fancy way of saying we want to move the graph left or right. It's just a horizontal shift. Okay. Well, you'll notice in these previous examples, I was multiplying by x. Here, I'm adding and subtracting. So it doesn't matter if you're adding or subtracting, if you're multiplying, or if you're doing both. We're still going to use the exact same expression, the same strategy for figuring out the points on the transformed function. I'm going to start with 0, less than or equal to 2 pi. What do you think is going to go between them? X minus pi. Whatever is inside your function will always be put between 0 and 2 pi. All right, so this is where we'll pick up tomorrow. Or, well, actually, no, Thursday, because I won't see you tomorrow. All right, so you guys have a great day. I will see you Thursday. Oh, that's weird. Okay. Okay.